Now in the last video that I said that the gradient of a curve at a particular point is equal to the gradient of the tangent line to that point. So if I can find the gradient of the tangent to a particular point, then I know the gradient of the curve at that same point. So let's see if we can use that information now to find a function that would give the gradient of a given curve. So let's say we have an equation, let's say y equals fx. And let's say I want to find the gradient of this curve at any point. So what I'm going to do is I'm going to pick one point, and these are my x and y axis, and let's say this is what my curve looks like. I'm going to pick up arbitrary point on this curve, and I'm going to call the x coordinate of it x. I'm calling it x instead of one particular value because now this point can be anywhere on this curve. Now to find the gradient of this curve at that point, all I got to do is to find the gradient of the tangent line to that point. Now I know one point on this gradient line, but we know that to find the gradient of a straight line, we know the gradient of a straight line is given by y2 minus y1 divided by x2 minus x1, which we also said is that is simply the change in y divided by the change in x. Now for this straight line, for this tangent line, I only know one coordinate. I know the x coordinate, and at that x coordinate, the y coordinate would be equal to f of x. So that's the value of the function at x. So what I'll do is I'll just pick another point on the curve and draw a chord through that point, draw a straight line through that point. So let's pick this point here. Let's say this is my point 1 and this is my point 2. And I'm going to call the x coordinate of that point x plus h. Or to put it another way, all I'm saying is that point 2, the x coordinate of point 2 is a distance h away from the x coordinate of point 1. And I have a line that goes through these 2 points. Now when x is equal to x plus h, then the y coordinate of that point will be equal to the function, the value of the function at the when x is equal to x plus h. So that the y coordinate will be given by f of x plus h. And now since I know two points on this straight line, on this second straight line, I'll call this tangent line t. That's my tangent line. I'll just mark it with a t. Now on this straight line, I know 2 points, so I can find the gradient of this line. Now the gradient of this line will be equal to y2 minus y1. Now y2 is equal to f of x plus h. That's the y coordinate at my second point. Minus f of x, because the y coordinate of point x. So y1 is equal to f of x divided by the difference in x, or x2 minus x1. But I've taken that distance to be equal to h. So the change in x is equal to h. Okay, so this equation gives me the gradient of this chord here, but what I wanted was the gradient of the tangent line. So what I'll do is, let's make h smaller. So instead of picking the second point over there, what happens if that second point was over here? Or in other words, I say the distance h is now reduced to this distance, so that such that the x coordinate of this point is now equal to x plus h. So if I draw a straight line that goes through between these 2 points, that's going to be a straight line that looks something like this. So that's a straight line that goes through those 2 points. This formula here now gives me the gradient of this line. So let's call this line 1 and line 2. Now, since I made my h smaller, this equation would give me the gradient of this second line. And graphically, you can see that the gradient of the second line is closer to the gradient of the tangent than the gradient of the first line. Because we said that as the straight line gets steeper and steeper, its gradient increases. So the line 2 has a gradient much closer to the tangent line than of line 1. So what happens if I make h even smaller? Let's say I move that point 2 over here. So as I move h closer, this tangent line, this line 2, approaches this tangent line. And when h approaches 0, we call this taking the limit. If I let h get so small that it's approaching 0, this equation here will give me the gradient of the tangent. Well, it would give me the gradient of this line, of this chord, but since that second point is so close to h, the gradient of that line will be equal to the gradient of the tangent. And we write that like this. We say when we take the limit as h tends to 0 of this equation here, of f of x plus h minus f of x divided by h, that would give me the gradient of this tangent line. And if I know the gradient of this tangent line, then I know the gradient of this curve at this point x. And since x was an arbitrary point, now I can work out the gradient at any point on this curve simply by putting in a value of x. And we call this the gradient of a curve. If y is equal to fx, it's usually written as dy over dx. And all that means is it's saying the rate of change of y with respect to x is given by this equation here. And if you are told to find dy over dx using first principles, this is the equation that you would use. And in the next video, I'll use this equation to find the gradient of the y equals x squared curve.